Hello, everybody. My name is David Malloway. I'm an educator in multidisciplinary engineering. I'm a former Toyota engineer. I have a master's degree in mechanical engineering from Texas A&M. And today I want to introduce to you, actually, I'm wanting to share with the broader audience something that I was beginning to share this morning with Dr. Zabuka. This gentleman, Dr. Gaius Zabuka, is in Nigeria at the Futo Federal University of Technology, Owerri. He's also with a background in mechanical engineering. He's leading a lab setup of the Scuttle Robotics Nigeria, which is located at an institution that's public. They have delivered education in engineering for many years at the university, but we have something that's somewhat new across all universities, and that is the support of physical hands-on undergraduate level and research level creation of robotics things, and really multidisciplinary is the key word. So you have systems that are including electronic systems. This is the background of my advisor. Starting with electronics, where electrical is just things that are powered by electricity. Electronics is when you have added, this is my personal definition. Electronics is when you have added computing, some microcontroller or digital logic, or maybe even breadboard-based analog logic to the electrical system. So electronics, this was a long-standing department at Texas A&M University. I think more than 50 years. Electronics have been prevalent, so the electronics bachelor's degree had been prevalent. And my advisor, when I came to Texas from my master's degree, was Dr. Joe Morgan. And I had wandered outside of my building, outside of my my discipline area of mechanical engineering to find, well, unexpectedly, I found a laboratory run by Dr. Morgan that was just thrilling. As soon as I walked in, I saw 100 different projects all over the shelves. So I'm going to screen share a little bit, and I want to use this. This is in the Vermeer Hall at some stage when they're moving equipment, but this was where a lot of us spent time around. For me, it was 2016, 17, 18. I went on from my master's degree to become a staff member here at Texas A&M, and Dr. Morgan was essentially my direct report, the person I reported to for a couple of years before he graduated. Now he became a faculty emeritus, and so the purpose of this video is to describe and just tell the story in general of a functional model for having a sustainable multidisciplinary lab where students in the undergraduate or graduate space at a university can apply their theoretical knowledge. They can produce refinements of projects that were either previously funded projects that we want to implement or instantiate on our own or pivot them. A chance for students to gain hands-on experience that is not limited to the number of hours available in the classroom, or not limited to the budgets of the tools of their own hands-on, their own personal projects. Like some students are out there in their apartments building drones and things, and they have a passion for their field, and so they're not just doing the classroom work. What is unique is that if you lead a lab such as this one, as Dr. Morgan did, then you have the chance to create a continuity from semester to semester, so that several projects and they become continuously improving. So you have a Kaizen factor. You create an opportunity for leadership, and this sort of happens naturally. So I think Dr. Morgan, for the most part, was not creating this structure of how everything worked, and that I will describe. I don't think he was deliberately making each of these things. This was more than a decade where he supervised this lab, and it happened naturally. But now, to me, all of the activities and the interactions are are fairly normal. This is how things work when you're building in a certain range of spaces. That lies in the extracurricular, and it lies in the applied. That is applied version of your in-class curriculums, and it lies in the intersection of small businesses slash outside entities, commercial space, and the university, where relationships are built in this lab between, let's say, an outside company that wants to be the recipient of some technology integration thing. They're willing to accept the student and research grade level of robustness in order to receive some innovation and try it out and build on that. They have budget. But yeah, there's a unique thing at this intersection. So in order to start it up, in order to make this stuff happen, then it's good to have a model. For me, it just happened naturally as I was exposed to this. And for many people, I think there's loads and loads of universities that they have a professor or more or staff member who would love to support this kind of thing. And they don't have a model to go off of. So I just want to do some storytelling. What you're looking at right now, I'm sharing my screen, and this is just an old panoramic photo that I took when things are a total mess. I'll try to open up some more photos and show and tell. But basically, you'd have let's say 5 or 6 ongoing projects. Let's say around 3 per semester, and you have around 10 students, each of whom volunteered or they sought this out, and they bumped into their students who work here and took an interest and showed up, knocked on Dr. Morgan's door and said, hey, can I work here also? And then find out the rules, and the rules have to be developed by someone. So I'll talk about those. Basically, here, let me pause and switch some images. Okay, so I just put in the keyword pick. That's a product innovation seller. We named 2 lab spaces. Well, Dr. Morgan did. This is the pick area. That is it's a hybrid. It turns into a working space for senior design teams in electronics, and also a multidisciplinary. The MXET, that's multidisciplinary engineering technology, that is newer. That one began only 2017, 2018. All the bits for ABEC accreditation were coming together. But this is next door, and this is very reminiscent. The modular table spaces where students can work so that they can break off into multiple teams, work on independent projects. Each of them have a whiteboard or more than one whiteboard. Each of them have power available. You see some of these power plugs dropped down. And so this is, what does it take to create a space that allows for multidisciplinary efforts? We have separate rooms where some mechanical things happen. So heavy amounts of filings. Let's say you're filing copper, aluminum, or cutting things that super loud noises. Those are in a separate space, but that space is smaller, and this is the main place you'd walk in to find people. We have this conference room. These are not absolutely necessary things, but this is just part of the story. Conference room where student teams, now this is for mainly for their curriculum-based activities, to give reports. It was quite formal in the capstone projects that there's a weekly meeting or more where the students organize into their respective roles and report out using slideshows or PowerPoints, etc., and talk through their technical details. So first thing to say that would be a standard is you need to have at least one faculty member who truly does have these 2 experiences. One is to physically, hands-on, be able to construct, build, design, test physical engineering devices. Okay, that's an absolute requirement. And that's some amount of experience in the professional wheelings and dealings of interfacing. So, for example, if a small business approaches to say, hey, can we sponsor a capstone project, or can you do this project in your, why would we want to do this in Dr. Morgan's lab instead of capstone? So capstone is 5 students, 1 semester. You get 1 shot, and it may or may not succeed. Sorry, it's 2 semesters. Many capstone design teams for engineering universities in general. Those are 1 semester, but this one's 2. So a business approaches and says, well, how much does it cost, and what information do we need to supply to the students to request a project, and how are they graded? What's the criteria to see it done? Well, MISL, this is MISL, something Integrated Solutions Lab. That's the name of the lab where we had ongoing student workers. So that means they had a very minor position. It's not pay and benefits and everything. There's just it's like a part-time job. There's an hourly pay. Okay. So Dr. Morgan's here on the left. This is a gentleman who owns a business that does engineering manufacturing, and they're talking about a sensors project. So first, the business person needs to have someone to talk to say, they need to know what are the skills of the team that's available as the team continues to change. So that the professor can say, yes, we can support this project, or we can support this part of it, or you could expect this level of outcomes to happen. So he needs to know the students, he needs to know prototyping, and then he needs to know generally how to professionally negotiate, which is it doesn't automatically happen. And of course, none of the activities are permitted to interfere with the student's actual 4-year degree program. So we're not taking anything from the curriculum. Again, MISL, the Solutions Lab of Dr. Morgan that I'm referring to, this one is an extracurricular. Okay, and through the projects, it ties back into the capstone projects or etc. I initially started talking about hiring. What was the model for student payment? Oh, well, this is a pretty good example that can link us. If the professor is very, very experienced, then you can very easily wind up collaborating with very big, powerful institutions like this is NASA. And so you're looking at a woman named Kristen, who is one of the scientists at NASA. Conveniently, they're only 1 hour away in Houston, one of the large NASA campuses. Okay, but then they have requirements to allocate a certain amount of budget and annual man hours to interact with education, since it's paid for by tax dollars. Okay, so these institutions like NASA want to come do a collaborative project. Their project must fall within the skill sets of the students, and they must fall within the capabilities of the labs that are going to produce things. So yeah, just to basically do the planning and outline of what to expect from the students, this is important. And then regarding payment, we had essentially some period where the student becomes a volunteer. It's a liability as soon as you have a student that has access outside of their class hours. That's typically 3 hours a week in the classroom/lab for any given curricular course. Now, outside of those hours, the student will have their badge access depending on the hours of access, and they'll walk into this lab and they'll continue a project that happened in between courses, or that happened with the other team members. So now the students are taking responsibility to show up during a time that is safe and reasonable, and then they're logging their hours. The first several weeks, I don't know what the amount of time was, but they would work as a learner/volunteer, and we're making sure that they're not too big of a liability. If the student is breaking things, or if the student has misplaced components, or if the student performs work that creates more backwards progress than forwards progress, then clearly there's a big cost associated with having that student, and maybe they're not a good fit. Alternatively, you have the student manager. So there will be one selected student who has worked there, hopefully 2 years or more. They're familiar with the assets and the materials, with how to order components. And then that student manager is assigned, and hopefully you keep them as long as you can. Sometimes they wind up in grad school. They could stay an extra year in the lab. They are the ones that give direction to the next students. They're telling, this is how things are done. This is what's relevant this semester. So there will truly be 50 different projects on the shelves that are stored away from previous years. And some of those projects get pulled off the shelf to be made into the present year's project components. I'm jumping around a little bit, so try to stay with me. This is photos from my 2016 prototype of a small satellite that was the requirement for my master's thesis. Okay, so my personal project related to the chassis and the energy planning design for a prototype. Here's just a number of simulations and experiments, machine shop, etc. So as a mechanical engineer, I was making this mechanical thing that's a completely independent project. And then in parallel, the MISL student lab under Dr. Morgan had several students that were in the electronics program, and they were designing this really specialized board. And so this was intended to be the motherboard of this satellite. And the students were generally juniors or seniors or fifth-year seniors. Sometimes graduation happens slower because student fails classes, and sometimes they really drag it on because they love working here. So anyway, the payment, the cost of the student should not be a factor in their decision to be involved in this. They should be very aware that the opportunity to touch these super high-tech solar panels that came actually from NASA, and the opportunity to have their name on a project that winds up on the space station, or anything that has some clout, is much more valuable than a $20 an hour salary or something like that. After the incubation period, then the payment for the students was minimal, just minimum wage or something like this, and it was self-logged hours. So this team, DVDT, was the name of the team that they formed. These guys formed this team for their capstone project. So their 4th year electronic systems curricular project, but at the same time, they were all night long showing up at the MISL lab to have access to all these tools and components to refine their design. And their design, the sponsor of their design was a small business that contracted jobs from NASA. So this also converged the master's project that I had. And so you have these various deadlines of students. Projects are always demanded for one course or another, or one degree or another, and having the MISL lab was an opportunity to converge those efforts, so that instead of making 5 average inventions, now we have one really great one. And then we can allow the freedom of, since the lab goes on year after year after year, we have the freedom to say, well, this gentleman is going to have an output that completes at the end of this year, and the students won't graduate till next year. And so that creates a continuity of communication. You have the master student, in this case it was David. We had David, these gentlemen graduated before me, and so I spent a lot of time just simply communicating and understanding the outputs of their design, so that nestled better into documentation than a raw, plain senior design project. And then they communicated quite a bit of information to me, so that as during my master's efforts, I had a better picture of the full story. And so going in and out of that lab, and then when I went back to the MISL lab and I checked in on the new students who had shown up the following semester, now they ask me questions and I can answer them. It creates a community, an ongoing sense of knowledge. And so and then they become friends. People become friends, so they exchange their phone numbers, and you really have a community. It's not just like these people are here just for a class. They help each other answer the questions to get better designs made. They help each other get contacts. So two of these gentlemen got hired by Texas Instruments. Texas Instruments was also a sponsor, and Dr. Morgan overlapped the two needs. So Texas TI wanted to introduce a certain one of their embedded chips into the student labs, and they were paying a sponsorship in the form of loads of materials, like big sets of the prototyping boards for this chip, and then these students integrated the chip in their senior design project. And MISL was the place where you could at least get some answers about every different aspect or each different person. You could trace down an email of a person who graduated 2 years ago. Anyway, regarding employment, so if you're spending time in this lab, you're an undergraduate student, and you have the chance to have your face and your name seen by the employers who show up periodically. So Texas Instruments would have a representative for their student activities, and they show up a couple times a year, and then NASA people show up a couple times a year, and then they get to have very low pressure, fluid types of discussions where someone in the company gets to know someone on the campus, and that student may wind up with the job after that. And also people just find their path. They find, if you were in a lab after school for a year, full of students that are all in the same degree program as you, but they're working on a multidisciplinary project, then you get to start to have a sense of whose skill sets, what's an ever skill set, what's expected to be known by everybody. Like mechanical, electrical, and software people, we all need to know a little bit about lithium batteries, and those are the things that become evident to you while you're spending time in that lab. So that's just, if I hope that doesn't sound off topic, that's a relevant discussion about interactions, basically. And then we could talk about supervision. No, I made a little note here to talk about supervision, but I just stumbled on these photos. This is some information. Here's me looking goofy, but we're at a conference for it's a space something conference. So even the undergraduates that were part of this sponsored team and part of MISL, they got to have this free pass to come to the conference. And that's one weekend that just with an explosive amount of information that they download into their brains about how the industry works and who are the players and what size of companies do which types of roles. And free tickets wind up happening all the time. So either a corporate sponsor invites the supporting team to come participate at their booth, or maybe there's an educational discount within the conference itself, or by so many mechanisms, there winds up being these passes available that could be valued at $1,000 available to the students that are inside of this organization, MISL, and then it's the value is so much higher than an hourly payment that you could provide, and the students are smart enough to know that is valuable, especially after they have they stumble into one or two students that are part of the organization this year, then they wound up being part of the organization and not worrying about what it costs them. So budget-wise, I think that, I mean, in certain instances, there's a requirement to list the hours and budgeting for a specific project. That's the responsibility of the professor to deliver to the sponsor of a project. And in that case, the students are, there's a planning at the start of the semester led by the professor, or maybe a graduate student who's leading the project, that in that planning they they allocate a certain number of hours, and then the students work up to that amount. And then it's a separate decision on what payment will be given, because it's an educational experience. It's not necessarily a job, and they're not carrying. Not paying the students is completely ethical. You have to. This has to be looked at case by case. But the student's salary being in an extracurricular project is a completely different decision than the arrangement that's made to the business. And so that gives the freedom for something. Let's say the rates of paying the students every year, every hour, can remain consistent, while the project's incoming fees, the money that comes into the lab that supports buying the parts and the materials and tools and hours of students, that incoming revenue may be up and down, but the student rates can remain consistent. That relieves the professor of having to try to sit down and budget that every year. The purpose of these labs, a lab like this, is not to make money. It's the budgeting is only done to comply with the university rules of activities on campus, B, to make sure that the costs are covered and there's enough money in the academic account that's going to pay for next year's tools and people, etc. This is a fun one. So once again, an ongoing project at the MISL lab led by Dr. Morgan. We have some of our STAR students that came along with myself. I was a STAR student. To National Instruments. So this is a meeting room of National Instruments during a time that we had MyRio being integrated in some lab equipment. So we have one curricular lab called Dynamics. And so in the Dynamics course of Electronic Systems degree program, we're implement the regular semesterly lab, where it's just, let's say, 7 weeks of planned, predefined activities and submission. So I'm talking about the regular curricular stuff. We are going to implement a lab with one standard computing device. It's an embedded computer that samples, and it'll either drive actuators or it'll take samples from sensors. But then getting familiarity with that, I'm holding my hands up to say, okay, it's a module this big. That's a flagship student product from National Instruments that's being integrated. But during that 1 year, when the device will get integrated into the regular lab permanently, some students will lead that and support it. So it's not all on the shoulders of the professor, but having MISL is a place where he can simply snag one of the 6 student workers that semester who knows about this type of software and say, hey, I need you to allocate your hours this week to make this thing happen. And then that packaged outputs of software and plans, or a little prototype gadget, can be the template, normal, continual device that's used as lab equipment every semester. All right, I hope I explained that in a way that makes sense. But the interest of NI was to be the company that carries the software and the hardware that all the students in that specific dynamics course get exposed to. The purpose of this interaction was to tie off loose ends in technical questions that we had about. See, this is a little off-road robot made by one of the former students. By the time of 2016, a former student had graduated. He was still into mechanical stuff. He built a set of these. And that same machine used the NI MIDAC device that we would use in our labs. And then we used, I invented myself for this undergraduate lab called Dynamics. I built a pulley and wheel mechanism driven and measured by the MIDAC. So you had this device that sits on a table that serves the function of one specific lab lesson. It's integrated with the NI device, and then so now you have the interest and the support of NI. You're not just any customer. Now you're the customer that's supporting one of their annual goals of getting this into classrooms. And so if we needed a phone call, we had a dedicated person who was up to speed on our project, who we could exchange information or little software files by email. And then we make sure that when we design our lab equipment, it is not gonna fail due to one little small software hangup. We have the direct support from the people here. And then planning, I think we were here to do planning of, they had an array of 3 or 4 different other machines that are more industrial, and they were thinking of donating those. We're talking like $15,000 per unit. It's an industrial controller that you would find in. Well, that's the natural next step so all these embedded devices, these little microchips that cost like $10 on an Arduino or $100 on a sampling device, they each of those devices has like a sister or a big brother that's packaged as a industrial product by these big companies that offer the chips, supported by the companies, and that's come with firmware and software by those companies. So there's, I mean, the more I talk through this, the more I see it's almost a huge missed opportunity to not just have a lab. It's great things automatically start happening, and the word gets out very rapidly just by having this lab, regardless of the budget you have for the students. And then the students are really managing themselves. They learn from the older gentleman in the lab. Whoever's the older student is showing how do they schedule their time, how do they make a purchase order and get permissions to use the academic budget for that lab to get new sets of screwdrivers. What do they do and when parts are failing, and instead of just replacing it back in the bin? They're learning real life stuff. They're meeting these professionals at these real companies. They're enhancing each other. The students are, and there's just so much to be gained besides a dinky payment that's the same. That's like working at Domino's pizza delivery. Okay, this is myself at a desk that I got my very own got my very own desk space at the university under Dr. Morgan. And so this particular space is not inside of the MISL lab, but imagine you have only 4 permanent desk spaces. This is all happening in one room at the minimum. Like this whole scenario can be built out of one room, as long as it's not. It's a space for everything except for a pure classroom, because there's not space for 30 seats. Okay, so you have 4 desks or so. You have your student manager who's allocated to one desk, so he can put things in between his lunch hour, in between his classes. He can set things down there. He has access, he or she. And then one semester, I'm speaking from the perspective of the professor. Now, a grad student shows up who's going to do a project that's value add. He's automatically got more responsibility and understanding of how things will work. So I put together this toolkit, this tool box. I tried to zoom in. There we go. Okay, so there's me at this desk that I was just handed. We keep 1 or 2 desks available all the time, except for really busy moments, where the professor can just snap his fingers and say, yep, okay, this is your desk for the next year. And now productivity just goes through the roof, because if you're academic, you know that most students on a campus do not have a place they don't even have a locker. Everything that they use to make progress on stuff is in a backpack or is in these temporary spaces and it's much harder. So Dr. Morgan said, okay, you're going to just grab whatever tools you need for this semester's work on this project. You're going to load them into this toolbox. He just passed me the toolbox, and then I bring that to my desk, and then I've essentially checked those out for the semester. We're more than responsible enough to make sure that things get put back, etc. we don't really have a concern with theft in those types of cases. You need to make the students aware that every $10 item is truly valuable and worth not losing and worth not breaking. Develop a process for who are you going to report this stuff to if something breaks and you need a new one. And that's a lot of that is the role of the manager, the undergraduate senior level student manager. So I could just, if I have need an extra tool to work on this project, I don't know where to find it in that lab, then I would just go pop in when the student manager is there. By the way, he's there at least 6 days a week, and some chunk of the day it's easy to run into him and ask questions in person. Much easier than it is to find Dr. Morgan in person, or a faculty member who's quite busy, who has a separate office. So I get my questions answered, I get my tools pulled together, and then I'm making progress for Dr. Morgan. The goals that I'm working on are going to serve my master's degree requirements and serve the MISL lab at the same time. So, yep, then we wind up with spare keyboards and mouses and different things like power supplies that are ready to go at any moment, that just really help. A great deal of multidisciplinary projects will require these little odds and ends that they do stack up in cost, but more importantly, they stack up in the amount of time it takes to go do purchase orders. Through the university is probably 3 times more complex than just making an order of a personal project, and not having to do the purchase order of a few AA batteries or screws is a crucial thing. That's part of what makes this lab work. And then, and if you cannot offer a permanent, somewhat secure desk space to a grad student, then you can't get nearly as much good outputs from them. So it's a win-win for everybody. Oh, and then as a grad student, I had funding for my project. It was really just paying for the academic costs. I didn't cost any money to the lab in this role as a master's student, and I didn't cost any. I didn't produce or take. There was no funding except when Okay, so I'm a mechanical expert among electronics experts, and so there was a few instances where I saw their tool, the hand tool or a drill or something like this is not the best selection, and we should upgrade it. And then so Dr. Morgan or whichever faculty can trust my judgment to say, hey, we really ought to get this, because it's not just going to be useful for me, it's going to be useful for everybody. And then very swiftly, you have basically students that show up and they start to understand the inventory of your space, and then when they make a recommendation, it's an informed recommendation, just further and further offloading of the weight of doing those types of administrative things off of the professor. Okay, I found this photo. Left hand, some of the small, new, affordable Tormach machine we pulled in. We were able to place it in the laboratory adjacent to the MISL lab. This is the ASEP. That's the ASEP is the name of this 4-wheel machine that was in a project that lasted a couple of years. And then from this vehicle, I pulled off the spring mass damper system that created a standard repeatable lab. So now you're looking at a simple stepper motor and a spring. It's a shock absorber from a remote control car type of system where, okay, we're going to have this oscillate up and down, and it's going to apply a force, and then we measure this force. And the whole lab was for you're going to learn how this sensor works that measures strain or pressure. We're going to learn about the reaction force of a damper, a liquid filled with oil and a little plunger. So multidisciplinary is great because we can borrow these components from any machine and put them into any other machine. And let's say me alone, I couldn't put this together, but with the colleagues in the lab, I figured out just the last couple of things I need to know in order to design and build this. And these blonde are the ivory colored parts. These are 3D printed, and these were some of the very first parts that I ever 3D printed in my life. And then we had someone that already has experience with 3D printing, actually almost all of the guys in that lab. And so just learning how to be capable happened like 10 times faster than if we didn't have the people around. Okay, and then so that's a lab apparatus the university gets to keep. It costs pennies. Like actual purchases made just for this were probably less than $25 in total. And if you wanted to purchase an academic equipment to put in a lab for student learning and engineering, you're looking at over $1,000 for something that's offered by a company for that purpose. And so the engineers themselves can be making the things that are used to teach in the labs, and they can be enhancing the things that are already there. And so from Dr. Morgan's perspective, we've got all these electrical guys, and we bring in the mechanical guy, and then suddenly there's these big enhancements to some just small little areas that didn't have a mechanical expert ready to set them up. Then, well, I guess let's just talk about the bridge from Scuttle to this lab, how it all goes together. Okay, so if you want to have an academic lab space where there is multidisciplinary engineering taking place with hands-on projects, so you result in experiential learning, you just need to have at least one robotic thing, because a robot is all of the disciplines put together, software, mechanical, and electronics. And you need to have one machine that includes all of those. Sorry, this is ideal. This is the essence of Scuttle. Its design is because it includes all the fundamental building blocks, but each one is accessible, modifiable, and documented. And so Scuttle itself is an educational tool, and then separately it's a platform that you can add on to any robotic stuff, have it controlled by this platform. But we need to have one lab equipment that people gain familiarity with, and that includes all of the basic, affordable, flexible, fundamental components. This is curriculum building up. Okay, and so even a 3D printer itself is very close. It has sensors, it has mechanical parts, it has hardware. These all need to be rapidly accessible, available, and known by the students in the lab. But then having continuity is the other part. So we need to be able to produce more than one copy of this thing, and as many as we need. We need to be able to have the documentation behind it, so the students can crack it open and self-discover that all the learning does not come from the professor. It comes from the internet, which has all the knowledge you could want, but now we have a lab equipment that creates a context for that. And so Scuttle is great as a platform for you to build every semester, build new projects. Let's say we're just doing we have a bunch of students that are experts in AI, and they're learning and trying out new stuff. Well, where are you going to try out the new stuff in the physical reality? You stick it on top of a Scuttle, and you invent a mission. Like, it's going to cruise through a factory to find all of the boxes with this type of label on it, etc. Yeah, this is some cleaner shots of the lab that was previously MISL, and as Dr. Morgan retired to faculty emeritus, then it was made half classroom, half working lab, okay, with all the Scuttle robots in it. These get stored away. They're standardized. When things break or get misconfigured, then we know how to configure them back, and you can also adjust them back to a predictable starting point for the instructional portions of the lab. Now you're going to have instruction that matches the starting point of the semester configuration of that machine. Okay, and then the feature that matters, I think, a lot is that the costs and the resources are the minimal. If you have a full-blown robot that has all aspects of engineering in it, how can we make it the minimal aspects? And so We don't need to have a PCB fabrication store. Those can be ordered online and so forth. We don't need to have a full $100,000 CNC machine like they do in many universities. We don't need to have a $10,000 laser cutter. And so this is just some various graphics from different points in the timeline where we tried to share that. It's too much to share in any one single presentation, but so this is what we're trying to build. It's an enhancement for the existing lab spaces for the guys in Nigeria, but it also comes with enhanced needs. It comes with a backbone of documentation, of standards, of design and prototyping methodologies that gives the students the freedom to produce anything that they wish to produce or to branch off on any other type of robotics project. It's a fundamental thing from the educational point of view. Okay, I think I'll wrap up there. There probably were many more things to say and share about how the lab works. I think maybe that gave a sense of if you are a faculty, or if you're someone who runs a lab or wants to start a lab, then that maybe that will just spur some conversation about how you might go about it and have the lab sustaining itself. The students, when they're doing the things that they love, they are super cooperative. They come up with ideas on how to improve the situation yourself. The faculty members are no longer, if they were ever babysitters, then they're no longer that. And now the faculty begins rapidly every semester learning new things, because the students go off in every direction and they discover new softwares that show up online, or components and tools, and the faculty member has the pleasure of just showing up in the lab as a distraction from the everyday meetings and things, and the students are excited to report, oh, this is what we discovered, this is what we found, this is what we improved. It can become quite hands-off and just super rewarding. So, and it gives the students and even older guys that were in industry like myself a chance to really explore and show their maximum potential. So okay, I'll wrap up there. Thanks everyone. And yeah, feel if I've probably made a handful of mistakes and probably left out a few things, so feel free to add those in the comments. Maybe it would be worth a second go at this video and try to share a little bit more based on whichever comments and feedback show up.